All right, so let's work this problem. I want to find the shear force and bending moment diagram for this frame. Oh, I just realized something.
It's literally the same problem.
Yeah. Did I do this problem already?
No. It's built like it.
It's the same basic idea, but you'll notice that the beam, the BC beam, doesn't have a distributed load, it has a point load. So we've seen kind of one like it. The process is going to be the same. I'm going to find my reactions at A and D, and then I'm going to break it apart at D and C and find those reactions, and then we'll draw the shear force and bending moment diagram. This will probably take a couple pages to do. So I'll start by, I'm just going to use this structure, or this drawing, as my free body diagram for the reactions. So there's my AX and AY. There's no moment because it's a pin. And over here at the roller, I've got DY. And looking ahead of the problem, I'm going to want to put this as a concentrated equivalent force. So I'll go ahead and write that in. So the equivalent force will be the area under the curve. It's a rectangle, so it'll be base times height. It's 12 times 3. It looks like it's 36 kips. And halfway up, that will be 6 feet. So based on all that, I should be able to find my reactions. So I'm going to start by summing moments at A. So right-hand rule. Sum moments at A, make sure the structure is in equilibrium. And what do I have? Well, these two applied forces, what kind of moment are they going to create about A? Positive or negative with right-hand rule? Both negative. So starting with the first one, I'll have a negative moment created by the 36 kip force, the distance from A to its centroid, 6 feet. A negative moment created by the 15 kip force, the distance from A to its centroid, 4 feet. And then I got dy. With my sign convention, that creates positive moment. And that has a moment arm of 8 feet. So from that, I should be able to calculate dy. I don't know what that is. 34.5. Anybody else get that? Just to check? Yep. Thank you. And then we can sum forces in the y direction. I've got AY is up, positive. GY is up, positive. What else do I have? Oh, this 15 kip is down. So with DY being 34, looks like AY is going to be negative 19.5. We talked about one of these earlier. It's not uncommon that possibly this edge you want to have to pull down. That's a pretty big force. It's maybe like a wind load. And, it's going to try to lift your building up. So your foundation is going to have to try to hold it down. Okay, and then one more. We can sum forces in the x direction. Make sure that's in equilibrium. So in the x direction, I've got AX to the right. That's positive. My 36 kip force, which is the concentrated equivalent, is also positive. And you get 36. And I think that's it. So it looks like AX then will be negative 36. So I've got my reactions. Any questions about that? All right, so now we're going to break it apart here at B and C. And just thinking ahead, we're not going to want to draw a free body diagram of BC because that would have 3 equations and then 3 unknowns here and 3 unknowns there. CD looks promising, just like our previous example, and also then AB. So there's really no connection between these two except for the reactions. So we can do them any way we want. I'll just do them alphabetically. So let's look at section AB. So I'll draw the free body diagram for that. There it is. I've already found AY. It was negative, so it's acting down. And that's 19.5 kips. Now at B, I will assume positive BX, positive BY, and then right-hand rule, I'll assume a moment. And then we've got the same concentrated equivalent force that we had before, 36 kips, and that's at 6 feet, 6 feet. I think that's all we have, isn't it? We already know what's happening at A. Oh, I forgot AY. What was AY? 36. And it's negative, so it's actually going in this direction. Oh, so we'll recap again at A. So there's my AY, AX. There is no moment at A. It's a pin. And then these are my three unknowns there. So 3 equations, 3 unknowns. So I'm going to start by summing moments. And a good place to do that would be at B, at the actual cut. We know BX and BY don't create any moment about that cut point, so I'll just have the moment. And with right-hand rule, that's a positive moment, so that's the moment at B. About B, the 36 kip force creates what kind of moment? Positive or negative? Positive. And it has a moment arm of 6. Then this 36 has a negative moment with a moment arm of 12. And what else? Oh, the 19.5, that line of action passes through B, doesn't create any moment.
I got a question.
Yeah.
Our AX right here, 36 kips, it was negative, and we're drawing it.
Well, I assumed it was positive to the right,
Okay.
so I got a negative value, so it's to the left.
True. All right. So we're not in shear.
Well, we're not talking about shear yet. It's just the force.
Okay.
So it looks like the moment at B is going to be positive and equal to 216. I don't know, I'm guessing. No, 200 and... Yeah.
That's right now, it's
216? Yeah, I was right. And it came out positive. So what does that mean? That's the right direction. Does that make sense? Well, you've got you got a 36 with a short moment arm, and you got this 36 with a longer moment arm. So the balance is going to be, it's going to want to move, what? Around B, it's going to want to move clockwise, right? So the reaction better be counterclockwise to balance it. Since these have the same magnitude, this one has a larger moment arm, that's going to be the dominant of the two. And it's going to want to try to push this in clockwise around B. So we need to respond the other way. So that makes sense. Then we can sum forces in the y direction. So what do I have? I've got BY acting up, positive. I've got this 19.5 acting down, that's negative. Anything else in the y direction? Nope. So that's easy to solve. BY is equal to 19.5. So this element is in tension or compression?
Tension.
Tension. And then we will sum forces in the x direction. What do we've got? We've got BX, that's to the right, that's positive. We've got this 36 kip at the bottom, that's left, that's negative. Got our concentrated equivalent load, that's to the right, that's positive. And what else? Well, that's it. So it looks like Bx is 0. We're maybe halfway done. And we've been at this for 10 minutes. So now what do we do? You could now go to BC if you wanted to, because the things you assumed here on AB for B are equal and opposite on BC, and you could draw that free body diagram and find the stuff at C. I think in this problem, if given the choice, I would go straight to CD. It's the path of least resistance. You're not including previous answers in, and it'll just be an easier free body diagram to deal with. So I'm going to come over here and repeat this that we just did, and let's look at section CD. So I'll draw the free body diagram for that. We found the reaction at dy. It was 34.5. It was positive, so that means it's up. There's no applied load. And then I will assume Cx, Cy, and moment at C. And I'm going to now find those values. So just like we did in AB, it's probably a good place to start is to some moments at the cut where you took it apart, which is point C. So the moment I assumed here, MC, with my sign convention is positive, and nothing else creates moment. So MC is 0. There's no moment at C. Now we can check the Y values. So I'll sum forces in the Y direction. I got CY acting up. That's positive with my sign convention. And 34.5 is also up. So it looks like CY is negative 34.5 kips. So the section CD, is it in compression or tension? It's in compression. And then you can probably already see where this is going, but we'll go ahead and check it. If you sum forces in the X direction, make sure they're in equilibrium, all you have is CX. So again, CX is 0. So there's not much happening in CD. There's no shear, there's no moments, but there's an axial force. If we drew an axial diagram, it'd be pretty easy to draw. Okay? And now the fun starts. Give me just a second to do a quick little change, and we'll draw the diagrams. So I'm going to do the strategy I talked to you about before. I'm going to rotate these things to make for my benefit. So I'm now going to draw the shear moment diagram for section AB. I'm just going to rotate it. So here's the beam from A to B. And if you look at your notes, you'll see that the shear at A, which is AX, is minus 36, which would be up at A. And the shear at B, which was BX, is 0. So there's no shear over here on the end. The moment at A is 0. What's the moment at B? Well, remember, I assumed moment at B in this direction, clockwise, or right-hand rule positive, and I got a positive answer. So that means my moment here is still that, and it's 216 kip-feet. And then, of course, there is a distributed load, and the intensity of that load is 3 kips per foot. And that length is 12 feet. So now that I have my beam defined, I can draw my template, and we'll start by computing the shear diagram, or estimating it. All these units will be in kips. Don't forget, the change in shear is the area under the load diagram. So let's see what we've got. We're going to start with a shear of what? What kind of shear is this at B or at A? Is that a positive shear or a negative shear? That's positive. What kind of shear do we have at B? 0. And the change in shears under the load curve, well, the load curve is rectangular. That's easy area. It'd be base times height, which is 36. The load is negative, so 36 minus 36, 0. That works out. And now we know the slope of the shear diagram is equal to the load. So I look up here at the load. It starts at -3 and stays -3, so that's constant slope. So there's my shear diagram for AB. Now for moment, again, we can define a positive x-axis, positive moment. All my units will be in kip and feet. And now let's look at our moment. So what's the moment at A? Well, A is a pin, so it's no applied moment, so it's 0. What's the moment at B? What kind of bending moment is that? Positive or negative? Positive. That should be 216. And I know the change in moment between any 2 points on my beam is the area under the shear diagram. So looking at from 0 to 12, what's the area of the shear diagram? What's a rectangle? 1/2 base, 12 times height, 36. That should be 218. And that's positive, so 216. 0 plus 216 is 216, so that works. And I know the slope of the moment diagram is equal to the shear. So the shear at this point is positive 36, so I've got a positive slope. And it decreases to 0. So there's my 0 slope. So all I have to do is kind of sketch in that shape. And there's my moment diagram. All right. I can feel the end coming. So now we'll go to the last piece that we need would be section BC. So let's draw that. So here's the beam from B to C. I'll bring back our calculations so you can see them for a second. So here is B. So BY on this structure is going to end up being the value here. And I found BY, and it was positive. So it's up, right? Positive up. So that means equal and opposite, it should be down. And that's, what did I say it was? BY, that's 19.5 kips. And then I go over here and look at C. I can't really see it. If I look at CY, all right, what did I find CY to be? Negative 34.5, right? So that means it was down here, which means it's going to be up over here. Oh, yes. think for a second. Then what else? Right in the middle. You know what? I just realized I worked this problem wrong. Or did I? Hang on a second. I had a little brain fart. Did I account for this 15 at the beginning? Oh, good, I did. Thank goodness. I suddenly thought I'd forgotten the 15. That'd have been one of those like, oops, like one of those staying up 48-hour deals and realizing that's not a good idea. So I think I'm okay. We'll see. We'll find out here in a second. Okay, so what do I know about the moment at B? Well, I solved for it. It was positive right-hand rule of 216, so equal and opposite be in this direction. And what's the moment at C? Well, we solved it with 0. So I think that's everything we need on BC. So there's my BY value, my moment at B, there's my CY value, and of course CX and MC were 0. We don't really care about the X direction anyway. Okay? So let's draw that diagram. So I will start with the template. There's my left and right. I've got this point load. I know something's going to happen in my shear diagram there, so I'll go ahead and add that. What's going to happen in my shear diagram as I go from left to right? Yeah, I'm going to have a big jump in my shear diagram. It's going to be exactly equal to 15. All right, so there's my positive X. It's my positive shear. We'll do everything in units of kips. So what is the shear at B? What kind of shear is that? That's negative. So I'm going to start off at negative 19.5. The change in shear between any 2 points is the area in the load curve. What's the area in the load curve first 4 feet? No change. So it should not change my shear. It should still be negative 19.5. And the shape of the diagram is the load. The load is 0, so I have 0 slope. So a constant shear in that section. And then as I go left to right, what happens? My shear change is how much? 15. So I'm going to take 19.5 and I'm going to subtract 15, and I get 34.5. And the change in shear between these 2 points is the area of the load curve here, which is 0, and I hit negative 34.5. And I should have written that in at the beginning. What kind of shear is that on the right-hand side? That's negative shear. So it matches. And the slope of your shear diagram is the load. The load is 0, so I have 0 slope. And you get this kind of stair-step shear diagram. Okay, let's see if we can squeeze it in here at the bottom. So we're going to do our moment diagram now. Positive X, positive moment. All these will be in kip and feet. So what is the bending moment starting here at B? What kind of bending moment is that? Positive. So I'm going to start off at 216. What's the bending moment at C? 0. So the change in moment over the first 4 feet should be this area on the shear diagram. It's rectangle, base times height. So what's 4 times negative 19.5? 78. What's 216 minus 78? 138. So 216 minus this change gives me 138. And the slope between these 2 points? Well, the slope of the moment diagram is always the shear value, and the shear value is constant and negative. So here's a constant negative slope. And now the change in moment over the last 4 feet is this area, which is 4 times 34.5. Hopefully that's 138. So 138 minus 138 gets me to 0. That's great. And of course the slope of the moment diagram is the shear, and the shear is larger and negative, so you will see your slope increase. So although this is not to scale, it kind of gives the characteristics of the change. So now there's lots of questions I can ask. What's the maximum moment in the structure? Looks like it's 216, and it occurs at point B. What's the maximum shear in the structure?
36.
Looks like it's 36, and occurs here at A. What's the moment in the middle of BC?
138.
130. Is it positive or negative? Positive. So how should this structure deform? So BC is all positive moment, so you should see it kind of bending like this. What about this guy? Also all positive moment. Kind of interesting. And CD has no moment, so it should not bend at all. Okay? So that problem took 26 minutes.